So a little bit about the team. There has been, as in the field, a huge evolution morphing the team, and we have been moving from this resource constraint deep learning to perception to end-to-end, and more recently we are constantly evolving towards this joint optimization of the end-to-end optimization of the flywheel, which I think is super interesting and is what I think I'm going to share today, and I hope you all agree with me on how interesting it is. I think we don't have to say much. We have seen it here. We have seen plenty of companies driving around, at least in the Bay Area, there's plenty of them. And Jensen said recently, autonomous driving is finally here, right? So now the question is, how do we make this really a scale? How do we go from L3 to L4 or whatnot? And I do believe that to reach that point, and I'm sure that we will see here today many times, there's a few things that we need to take into account. First, safety, right? So for L4, safety is critical. The human is not going to be involved, so we need to be extremely careful. The quality of the system has to be outstanding, right? So that's also critical. Reliability and trust. The user needs to trust what's going on. And to get to that point, I think it's that there's a general consensus that there's a few things that we need to do, right? First, we need to handle the extremely long tail of events. That's one thing that needs to happen. No accidents, no strange situations, or at least we should be able to deal with them. In order to let's see, in order to deal with the generalization and the long tail, I think at this point we all agree that reasoning is the way to go, right? At the end of the day, we need to go from in distribution to out of distribution, and if we can leverage these reasoning capabilities of VLMs and whatnot, the foundation models, that would be amazing. As an example, and there's many more, right? So as an example, we were working on this idea of OmniDrive, a model that can explain what's going on, and we trained this model with some counterfactuals and whatnot. This is just one example, but if you walk around, you're going to see a trillion of them, including VLM, VLA, and whatnot, right? So what is next? What is missing? We know what we want to have, but there are two challenges that we should deal with. First, all these methods are based on end-to-end learning, and the paradigm, most of them is imitation learning. That's a problem because we depend on what we can drive. And the second is the so-called data problem, right? So garbage in, garbage out. So how we make sure that we get good data for training all models. So let's talk about the first one. And that's not what I'm going to talk about in the talk, but at least there's a huge amount of work that is based on trying to move away from imitation learning. Basically, how do we, How do we move away from imitation learning, and reinforcement learning is the way to go. Instead of imitating, we try to explore, we try to generate trajectories, score them, and see if by chance we get to see what we want. We get to find a solution. Reinforcement learning has a number of challenges that the community is dealing with. First of all, this scoring mechanism. If I have a trajectory and I do not have the human-driven trajectory, how good or how bad it is. In order to explore all possible solutions, we're going to have a closed loop training or some sort of way to truly explore during training. It's well known that there's a clear sim to real gap, right? That's something we need to deal with. And at the end of the day, if we really want to use reinforcement learning for training, we should have something that is fast and efficient for developing. The team has been producing some work, starting with Hydra, and has been evolving towards the idea of, can we produce a scoring in open loop that is based on some perception metrics that we can use as a safety criteria for selecting what, if we don't have imitation, what other trajectories would be useful, right? Here's an example of the work that we did for open loop evaluation that won the CPR challenge. what we were doing is proposing at the end something that is model agnostic, and given a number of trajectories, we can refine up to the point that we get the best one. The key here is reducing the search space so it becomes more efficient. One thing that it should be clear is that one of the challenges of reinforcement learning is what data do we use for exploring, right? So if we want to explore as many things as we want, if we have an accident, if we want to explore what could have happened, basically addressing that data and limiting the amount of exploration on all possible data points is critical. The second big problem is the data problem itself. And it's well known that either synthetic data or real world data are going to be key to achieve this, right? So we have seen plenty of works, especially on foundation models, that basically address the problem of data, and particularly on what data do we use for training, right? Now, the question is, do we need more data? Briefly, I do believe that there's several sources of data, particularly for AV. We have this collection, we have customer fleet, the fleet that goes out there, collects data somehow, and we have also all this dashcam data available in the internet. So more than do we need more data is how do we access to the right data for problem? For me, the data is there. Now, the question is, how do we access the right data, right? So we know that there's an exponential growth, and the moment we deploy our models in customer fleet, the exponential goes in, like, increases even more. If we are not careful, what is going to happen is that we're going to have an extremely imbalanced data set that is not useful for our purpose. If we think about nominal driving, that's going to be the majority of the scenarios. And what we really want is to deal with the long tail. So how do we find and how do we make a good use of that data? Obviously, and there's a number of people that will talk about this today for sure, do we collect or do we generate data? I'm not going to go outside, but at least inside the org, inside Nvidia, for instance, we have NeuRec, right? NeuRec is extremely powerful to generate a digital twin. We have some sort of data that we want to evaluate on or we want to train on. We generate the twin, and now we can generate variations in order to train or test our model. Also super interesting is this idea of Cosmos Drive Dreams, where, as many other generative models, what we do is we give a prompt, and the model, just given that prompt, generates some data that ideally is going to cover some use case for training. So the question again is the same. We have a prompt, we have a way to generate a digital twin. What data do we use? So what I'm going to do in the rest of the day today is talk about not the way we generate the model itself, but the feedback loop. I actually think that that's a critical component that we briefly talk, and I will try to convince you that if we focus on that, we eventually will be able to generate very powerful models. And in particular, if we automate that process and we add some reasoning capabilities, we should be able to move from imitation learning and the bottlenecks of reinforcement learning to a data problem, and from a data problem into a compute problem. And if we do that nicely, what is going to happen is that at the end of the day, we will have some self-improving agents that have minimum human in the loop. So let's talk about data, and what do we think about the data set that we are trying to add to our models? I actually did ask ChatGPT what's going on, what is a good data set, and this is what I got as an answer. And for me, the key relevant points are the data must be related to our problem and needs to be large enough and needs to represent, the coverage needs to represent what we are trying to address, the problem that we are trying to address. So in the long tail cases, for instance, we will need to represent some nudging when we are driving. That's a corner case that we should be solid. We should be able to understand the errors that the model is covering and then find the data that addresses that. And hopefully, if out there through the dash cam we see some accidents or whatnot, we should be able to have data that contrast these accidents, right? So we can learn also from that data. So data selection and curation is nowadays everywhere. And there's a lot of works to try to reduce redundancy, maximize diversity, and at the end of the day, improve the quality of the data set. For me, the key component of those works is how do we structure the training set? Can we actually go from an unstructured pool of data into some sort of a structure where each of the groups has a clear intention, has a clear semantic meaning, representing something that we would want to be good at? In our case, we have worked with foundation models to generate a text description that clearly provides what's going on in each video. If we have that and we pass that through a language encoder and we use some clustering, what we will have at the end of the day is a clear structure of our data set. Specifically, what we do is we get the video and we ask for a very detailed description of what's going on. In our case, we don't retrain or anything. We just use the foundation model as it is. And the ultimate goal is to leverage the generalization capabilities of these models. The less we fine-tune, the more generalist the model is going to be. So here we have some examples of one internal data set that we have, where we clearly see that the groups actually represent what we are looking for. At least they are meaningful. They are consistent among each other, right? So for selecting the data, what we're going to do is find the centroid, the point that is closer to the centroid, and those are going to be our main representatives, right? If we do that, what we found out is that at least for certain tasks, we can see that it's way more diverse. With less data, even in long tail cases, even in underrepresented classes, we will be able to get much better results, which is a good indicator of diversity in the data set. Interestingly, we can reduce the amount of data and still get good performance. So that's pretty good. And now if we expand our data sets, what we will find out is that systematically we get better and better results. Again, we are just doing a better job in curating the data set. Interestingly, this is not only for AV, but recently a sister team at Nvidia has also proved that this is very powerful in general for training foundation models. And at the end, the idea is how do we structure the data and how do we evolve that data while we train, right? So the question then is how do we use that powerful tool into the loop? Right? The main bottleneck usually is that this feedback loop is human dependent, right? So humans need to collect the data, human needs to describe what's going on, and from that, search for data. If we think about what we just shared, we should be able to characterize the data. If we have some triggers that says this data is interesting, is in an accuracy of our model, if we run through the agent through the VLM, we're going to get a description, and then we should be able to map those errors to training data that is of interest. In our particular case, what we did is with the internal loop, the implicit representation, we got the training logs, and we use PDM metrics, these predictive driving metrics, to flag what is not good, and with that, describe all the videos and find data that's similar to those videos. Basically, we go to a new pool of data and we try to add data to the data set. Interestingly, these VLMs are particularly good and are going to allow to change from just pure organizing the data. We're going to also be able to retrieve data of interest. We just do a random query and we're going to get data of what we want, right? Here are some examples of how do we get cut-ins, specific actions in the data set. and here's some other for stop turns and whatnot. If we do this and we go, we select the errors, we characterize the errors, we retrieve new data, and we expand our data set, what we observe is that we can actually do much better at correcting errors. So as you can imagine, if we iterate in the long term, we should continuously improve the quality of our models. Now, does this really work? What are the limitations of this approach? And three of them come to my mind, right? First, we are addressing one error at a time, right? And I think that does not scale. We should be looking for patterns instead. The second, the coverage of our data set might not be what we want, and I will talk about this in a minute. And the last one is we need to revisit how we are describing the data. This caption that we are generating, the description that we are obtaining with the VLM is very powerful, but might not be what we want. Let me go quickly through these points. The first one is scalability. Should we address one point at a time? If we do that, it's not going to scale, but that has a very clear solution. Instead of one point at a time, we can describe all the errors that we have. We can extract patterns, and now the most representative representation of that pattern is what we are going to use for expanding our data set. The intuition behind is that we will be collecting what is common to all the errors and not what is the nuance of the errors. If we think about how powerful this goes beyond our data set. If we think about the error problem or the data generation problem, now we have a clear indicator of what is the most common characteristic of the errors that we are representing. If we use that into our RL framework, intuitively, we should be able to correct more errors than before. What about the data coverage? I was saying that I do believe there's a mismatch between the training and what we want to address. And the reason behind is that in general, when we talk about data-driven methods, I do believe we think about, oh, I'm going to generate an amazing training set. And we usually keep the evaluation set fixed. I do believe we need to change that. Let me give you an example. This is what ideally we would like to happen. We collect some errors, we generate patterns. From those patterns, we try to map the centroid of the pattern, the most characteristic thing of those errors into my data set structure. And ideally, that's going to go into one cluster. We expand the cluster and we retrain again. And that's going to yield good results. If we don't find a cluster mapping, what we could do is generate data or any other thing, or try to go out there and collect more data. What really happens is that there's a mismatch. This idea that my error is going to be mapped specifically to one of the clusters, that does not happen in reality. What is going to happen is going to lie between clusters. It's going to lie in the middle of our representation. So if we think about this in the long term, at the end of the day, we're going to be expanding the number of clusters in a strange manner. And we learned in the past that if we don't take care of this, what is going to happen is that we are going to get even more unbalanced data set. Think about, we look for strange situations with pedestrians. Likely, if we go to a urban scenario, we're going to get more cars than pedestrians. So if we were unbalanced at the beginning, now we add pedestrians, but those pedestrians come with the scenes with cars, so this will be more cars, so this is a chicken and egg problem, right? Instead, the twist that I think needs to happen is, let's start with what we want to achieve. What is the set of long tails? What is the ODDs that we want to achieve in our model? If we characterize those, if we generate closed clusters for those, now what we can do is generate our data structure based on what we want to achieve. Once we have the data structure, once we have those clusters represented what we want, we remove all the test data, we remove all these errors, and now we go to our pool of data to create our meaningful data set. And that's a twist, but it's a very important, because now all our training data is going to be particularly meaningful to address each of the errors that we are aiming at, right? So this is how now it has changed. Instead of, this is how the loop looks like for implicit errors, right? We can have eval logs, and we're going to do the entire loop automatically. What if we want to address also explicit errors? Implicit errors are those that are through training, but the moment we deployed our models, that's going to be in the wild, and we're going to have other type of errors, and hopefully we should be able also to leverage any source of internet data, even if that data does not come from our sensor ring, right? So how do we deploy, how do we make use of this data outside the inner circle? Let me give you what exactly happens and what is the main difference. It's a nuance, but it's very important. So in this particular case, it's a prediction, which could be a disengagement, right? So we are driving, and the prediction says run over this pedestrian, which is unfortunate. So the person takes over. We don't have the right trajectory to imitate. That's a problem. Here's another example. We are driving. This is from internet, and again, we crash. So we don't have either a correction, or we don't have anything. We only know that we should not do that. So if we try to describe this data, the description is pretty accurate, right? They describe exactly what has happened. There's a pedestrian crossing, we are turning right. What is missing? This description is describing a correlation between two things. This description is giving us the erroneous behavior, something we should never imitate. How do we convert from this to something that can be used for training? Let me dig into this detail a little bit more. So the error that we have is we're going to make a right turn, and there's a pedestrian crossing, right? If we think about that description as it is, you can see that we have three possibilities, A, B, and C. All of them match the description I just gave you, right? In all of them, we are turning, and there's a pedestrian crossing the street. Now, if we use this for training, we are not going to get what we are looking for. The problem is that we are focusing on the correlation between pedestrians and ego movements. And what we really want is the causality. We need to reason what is causing the accident or what is causing the disengagement. So pragmatically, I have the same error. And what I would love to have is a similar situation where the car actually stops in front of the pedestrian. If we have many of these, what is going to happen is that our training process is going to be much better. And we will still be able to use the prediction error, that data, as test, if that makes sense. So what we need to do is we don't need to describe the data. We need to generate counterfactuals that dream or just imagine what would have happened in other situations. Let's think about this example that I've been showing you with the accident from Nexa dataset. In this case, we ask for a clear description of what has happened here. And the model or reasoning agent is able to describe the scene and also describe why the accident happened. And even gives us some reason. And so this is very powerful. But with this, we think it's not enough. What really matters is why it happened and what we could have done to make it, to avoid the accident. With that counterfactual, with that idea of what we could have done, what we can do now is either search for data, or in this particular example, try to generate new data and data variations that cover all these counterfactual that do not imply an accident. And that means that now we have proper training signal to keep improving our models. So at the end of the day, our training loop that was very simple with the humans involved could have, or feedback loop could have changed to something like this. Any log, any error, any disengagement goes through an agent that is going to generate the structure of the events that we want to cover. And with those events, we're going to use that structure to attract training data. When we try to find the relevant data, instead of using only the descriptions, we may use also counterfactuals, this idea of what if we have done something different. If we follow this, and we should be able to constantly improve the performance of our models. So as a takeaway from this talk, first of all, if we manage to obtain this automated flywheel, I do believe is a very powerful way to achieve a continuous self-improvement of any AI model. We think that if we want to achieve safety and generalizable AV, we should work together between jointly optimized data and models, not as we have been doing so far, that they go independently. We have also observed that foundation models and VLMs and reasoning models are very powerful in the car, but actually are extremely powerful if we move them into the data flywheel. And last but not least, to the data-driven approach, we have added two twists, a small twist into components. First, focus on data coverage. Make sure that the data truly addresses what we want to achieve. And the second, don't forget that it's not only the data we have, but if we can generate counterfactuals, that's going to be a powerful solution to keep improving our training sets. Of course, this is a bunch of work from a huge amount of people who I'm very thankful. And last but not least, NVIDIA is hiring. Patrick Janju is here, so please reach out in case you want to join. The family is growing, and you're